let's try a slightly different problem this time. So in this case, I have a diverging nozzle, like this. And I have a flow that is Mach of 2.2 and a stagnation pressure that is 101.3 kilopascals right outside of it. That's area 1. Call this area 2 because there is a normal shock standing in the entrance of this nozzle. And we want to know a few things. We want to know what the Mach number is at the exit, as well as what the static pressure is at the exit. Okay, so these are some valuable things. We need to figure out what they are, otherwise we can't solve this problem. Oh, and one thing it does tell us is that the area of the exit to the area of the inlet is equal to 4.0. Okay, 4.0. Okay, now some of these things we can do pretty simply. So first off, let's figure out what happens right after that shock wave, okay? What happens right after that shock wave, because that's going to be very, very helpful to us. So we have a shock wave, we know what M is, so we're going to go to Appendix B, that's the normal shock properties. And we're going to do it, and we're going to find out for a Mach number that is equal to 2.2, we want to know what is M2. We also want to know what P02 over P01 is. That will be very, very helpful for us. And we'll probably stop there for now. I think we can do it from there. That'll be okay. So let's figure that out. Oh, but before we do that, sorry, one question for all of you. From 2 to the exit, I'll just call this E right here, is my flow isentropic? From 2 after the normal shock until the exit.
So you're saying it's isentropic before, and then you're asking if it's isentropic after?
Like, it's not isentropic when it goes like through the shock wave, yeah. But after it's gone through the shock wave, is that flow isentropic after that point? You're right, yeah. So this is isentropic. This transition from 2 to E is isentropic, and from not moving at all, like off at infinity, to 1 is isentropic, but from 1 to 2 is not isentropic, because it has a shock wave. That's just important for us when we're looking up values later. We're going to need that information. It's going to help us out. Okay. So we'll go ahead in Appendix B and we'll find out what the Mach number 2 is going to be and P02 over P01. So I already got these tables up, but this is Appendix A. We don't need that one quite yet. Let's go over here. Beautiful. So we have a Mach number of 2.2. I go down here, and we need this third to last column and the final column when we're doing our values. I wish it traveled with it. It doesn't, sadly. Okay, so here's a Mach number of 2. So I'm going to go ahead and screenshot my screen again so that you can see exactly what line I'm looking at, and then we'll write down those values. So these values are what I need. This is the P02 over P01, and this is the second Mach number right there. Okay? I can't read problem statements. So this is the value we need. This is the P02 over P01, and this is our Mach number after the shock wave. Okay? Thank goodness. If only you had a teacher who could read. So P02 over P01 is equal to 0.6281. And let's see here. What was the shock wave? Actually, that was completely wrong. I switched it around. No, either right. Good. And M2 is equal to 0.5471. I think I did that right. So let's check again. I did. Perfect. Okay. So we have M2 going to 0.5471. It's looking good. Now, here's the thing. We know this is diverging. We know it is isentropic. Okay. Cool beans. But how are we going to find, as accurately as we can, what is this pressure and velocity at the exit? We're going to do it using a term that I don't talk about too much, but it's a ratio that you see in your isentropic flow table. So I'm going to go ahead and go to that table, and then we'll talk about it there, and I'll explain what it does. So let's jump back here again. Let's close this because I don't need it anymore. Okay, and we'll go back one. So there's this column right here in your table, which I never really reference a lot. It's A over A star. A over A star. And I've never talked about it too much because it's confusing to a lot of people, but we will see it in some problems, so it's good to see it in a problem rather than to talk about it in a class period. So A over A star is simply a ratio. It's the ratio of my area to the area when I am sonic. So when I'm going at the speed of sound. So if I am going right here, okay, and let's say that I am going sonic right here, okay, that's m is equal to 1. Well, and I know what my area is right here. Well, that would be A star. Okay, that's A star. And so I can tell what A over A star needs to be for me to accelerate or decelerate, depending on what's going on happening here. Okay, now let's go down a little bit and see that in a little bit more detail. So if I'm going to go down now. I'm going to go down to when my Mach number is equal to 1, which is right here. And you see that A over A star for a Mach number that's equal to 1 is, who would have guessed it, 1. Why? Because it's just the ratio of itself. Where I am going Mach 1, that is A star. Okay, so this is going to help us out here. Okay, this is going to help us out here. So we now know that this A star is a point of reference. It's a point of reference. As a note, it doesn't have to exist in my flow. It's just a point that I'm referencing everything else to. Because if I look at my flow right here that I'm working with, like when I'm expanding here, I am subsonic right here. I'm going to be subsonic right here as well because I'm expanding. It never hits sonic, but I can still use this as a reference point, okay? I can use this as a reference point since they're both going to be looking at it. And so if I'm trying to find out my properties, I can use A over A star to figure out my Mach number at some other point in my flow. Like, right here I can find my Mach number and all the other values using A over A star, just like I can use my Mach number to find my P2, P02 or P1 and all that stuff. But I don't know what my A over A star for my exit is because I don't know my Mach number at my exit. I don't know anything for my exit. However, I can know something else. I know that A exit over A inlet is equal to 4, right? And I know that if I divide both the top and the bottom of that by A star, I'm still fine. That's just, also I shouldn't put an E right here. A star is not connecting, it's just one its own thing. I would be fine, I can do that. So I know that AE over A star and then AI over A star is also equal to 4. Now I know my Mach number right after the shock wave, which means I can find out what AI over A star is. And if I know my Mach number right after the shock wave, that means that I can then find out what AE over A star is, and I can work my way through it. So what it'll kind of look like going back to that table is I'm going to go ahead and I'm going to go right to the right place for this, make it a bit easier. I think I can get enough things in here. That works. I'm going to do my problem something like this. As a note, there is interpolation in this because I'm going off of a different version. So what I have here is I'm able to, I know my Mach number, okay? This is like, M2. I'll go over, find out what A over A star is. I'll use that ratio to figure out what my A over A star is somewhere else. And then I'll go over and figure out what the Mach number is, okay? That's what I'm doing here, okay? That's what I'm doing for this problem. And it'll work very, very well. Issue for us, I've got a Mach number of 0.5471. That ain't on this table. It's not on this table, which means interpolation. Why am I doing this to you? I'm doing it to myself, dudes, okay? Like, I didn't want to have to go into a different gamma. This problem's supposed to be done for gamma 1.3. I have all my values then, but I'm just not working right here. Okay, so I'll need goodness. Make sure I pick the right values. Yeah, I'm going to need these two values. So 1.27 and 1.24. Okay, let's find out what A over A star is. So AI over A star, it's between 1.27 and 1.24, 1.27, 1.24. Did I put that in the right order? I hope I did. I did, nice. That's for a Mach number of 0.54 and a Mach number of 0.56. Okay, so I need to make an interpolation sandwich. Now, if you took my thermal class, you've seen interpolation so many times that this is like a piece of cake to you. If you haven't seen it before, well, you're about to see it. So here's how it works. If I want to find the Mach number, or the correct A over A star in this particular case, I do it like this. So AI over A star is equal to the low value. Does not matter which one you choose. I'm going to choose this is low and this is high because I'm basing it off the Mach number. That means that both these values are high and both those values are low. So AI over A star low, which is 1.27. Okay, and then I'm going to add on to that. So plus the difference between what I know and what I don't know, which is my Mach numbers here, okay? So that's going to be 0.5471 minus 0.54. That's the difference by Mach numbers, times the difference in my AI over A stars. So 1.24, that's the high, minus 1.27, all over the difference on the other side, which is 0.56 minus 0.54. Beautiful. And writing that out a little bit different way for you is, let's see, I'm going to say F for find, and I don't know, I'll just call them A and B. So this one right here is B, this is A. Just writing out an equation for this for you, okay? So B is equal to B low plus A minus A low times B high minus B low all over A high minus A low, okay? So I want to give you an equation for it so you would have a little bit easier time with it. You can choose, just B in this case is whatever you're trying to find. That column is what you're trying to find. Okay, I don't know what this value actually is, so I'm just going to plug it into my calculator now and figure it out and see what I can do.
Yeah, 1.2593.
I'm just going to trust you in that. You know what? I'm going to trust you in that. Okay, so we got AI.
That sounds right.
Sounds right. Over A star is equal to 1.2593. Now from earlier, we realized that AE over A star is going to be 4 times AI over A star. So AE over A star is equal to 1.2593 times 4. And let's see what that comes out to be. About 5.037. Okay, so now we have A over A star. We can then use that to find my Mach number at the exit. Okay, we can use that to find my Mach number at the exit. So let's go back to our appendices again and figure out what the Mach number is at the exit. So it's round 5, right? Okay. So that would be somewhere between a Mach number of 3.1 and 3.15. Now tell me why that's wrong. I purposefully am trying to confuse you. It's wrong. Yeah, that's horribly wrong. That's way off, like super far off. I'll tell you this, it has nothing to do with the value you gave me. Your number was perfectly correct. Well, let's look at our problem again, and you tell me what happens.
Because it gets bigger, so
it does.
To get faster.
So it's all based on our area Mach number relationship. Remember that if I am supersonic, or if I'm supersonic and I go into this, I will actually accelerate. I'll get faster. If I'm subsonic, though, I slow down. And so for this table, it's actually multi-value, which means that I can find the same value for high numbers and for low numbers It just depends on, was it subsonic to begin with or was it supersonic to begin with? You have to be careful with that. I know it was subsonic to begin with, so it means it's going to get slower in a diverging nozzle. And so I need to look at low values rather than high ones. So I'm going to go back down here to very small numbers and try to find 5, which comes at, I'm going to cheat here and say that it's a Mach number of 1.12, okay? It's not technically, it's close enough. So that's not quite right there, but sue me, I don't have to do a lot of this. Okay, and so we get P naught over P is 1.01. Mach number is going to be 0.12. So let's go ahead and write those down. So roughly from Appendix A, for a Mach number, for AE over A star, that's equal to 5.037. I get roughly that my Mach number is going to be equal to 0.12, and roughly that P naught 1 over P1 is going to be equal to 1.01. Cool? Okay. So we're doing pretty good here. We got a lot of values. We're almost to the end now. Okay, we're almost to the end. But we're not quite there yet. Okay. So now we need to solve for the last thing I asked for, which was what is my static pressure at the end. So let's try figuring it out with what we know, okay? Okay, so I have this section right here. I do know I have a 2 right here. I have a 1 right here. I know what P naught 1 is. That's all I know. Okay, I've got an E right here. Looks good. That seems fine. Yeah, seems fine. So let's see here. So I know what P naught E over PE is. I've got that. That looks good, right? Okay. Whoop. And let's see what else I have here. I also know what P naught 2 over P naught 1 is, correct? Okay, so that's pretty good here. The question is, what is the relationship between P naught 2 and P naught E? The key word here is that there is isentropic flow. If it's isentropic flow, stagnation pressure does not change in here, okay? That means that P naught 2 is equal to P naught E. Okay, let's see if that's enough. So PE is going to be equal to PE over P naught E. You already know that P naught 2 and P naught E are the same thing, so P naught E over P naught 1 times P naught 1. Hey, I think we have all those values. So let's plug them all in. Okay, first off, PE over P naught E, that's 1 over 1.01 because, remember I had to invert that. P naught 2 over P naught 1, I think we have that earlier, so I'm going to just scroll up and see if I can find it. We've been going for a while on this problem. That's 0.6281, there we go, we have it. And then finally, P naught 1 was 101.325 kilopascals. Okay, so with that, we should be able to find our static pressure right there at the end and see what it comes out to be. So let's try it. 101.325 divided by 1.01 and then times 0.6281, which comes out to be right around 63. So 63.01 kilopascals. Okay, there we go. Now that was a fun problem. Maybe not for you, but definitely for me. And we did it. We managed to solve it, and we got their answer. Big things to remember here is that A over A star is simply a way of referencing different points inside of a something that's changing shape, changing size, and how you can figure out the relationship between the properties based on a known reference point, and that known reference point is simply where the flow would have been sonic. And that doesn't have to exist. Like in this case, there was no sonic point in my flow. In some cases, there will be, and that's fine. It's just in this case, I didn't have one. I'm still referencing this theoretical one that could have happened. Like, if this had continued converging for, a long time, there probably was some sort of sonic point over here. Okay, we could have said that was probably what happened. It doesn't really exist, but I can imagine it happened, and that's why we're doing it. References are important. Cool. And when we knew that, we also knew the stagnation pressure doesn't change when we are in isotropic flow, and so that helped us to solve this problem much more easy. So, we got it.